scientists, and he won the IEEE CS Technical Committee on HPC Early Career Award as well for excellence in HPC. So really accomplished scientist, and we're going to. His research area is basically I guess the conjunction of LLMs, AI, serverless computing, cloud, and storage. So with that, let's welcome Yue Cheng.
Thank you so much for the introduction, and thank you so much for having me. And it's my great pleasure to be back at my alma mater. This is my very first time visiting this new Alexandria campus. This is just awesome. Great to see my mentors, professors, and also to see each one of you here in this classroom. So today I'll be talking about rethinking storage system design for modern AI models. And this is a project that we've been working on for the past several years. And I would just like to share some of the most interesting, most exciting research results with you all. You might be wondering what kind of academic preparation you might need in order to understand the research. Well, I would say this research process is purely data-driven. I've conducted lots of analysis, characterization study in order to better understand the data distribution, understand the system behaviors. And based on those observations, we propose very simple and yet very effective techniques and algorithms in order to tackle the research problems. Okay? So if you have CS bachelor's degree and you've taken 4 courses, you've been able to understand most of the research over here. Okay? All right. So let me start again with a very brief introduction. I'm an associate professor with UVA. I'm with data science and computer science. Before that, I got my PhD in 2017 from VirginiaTech. After graduating, I started a faculty career as an assistant professor in computer science at George Mason University. I recently just joined UVA in 2022. So if you take a look at this timeline, you will probably notice a theme, which is that I've been spending such a long time, almost 15 years at major public universities in Virginia. So I think it's especially meaningful for me to stand here to give this seminar at VirginiaTech, Alexandria campus. Another theme throughout my professional career is I'm a systems researcher. I'm a computer system researcher by training. My research interests include system for AI, AI systems, serverless cloud computing, data and storage systems. My current research focuses on building the next-gen AI infrastructure that power the AI applications used by millions of users. So my talk today will be primarily focused on the first direction, where we are rethinking the storage system for massive AI models. And my research has also generated some real-world impact. Some of the results have received adoption at real-world production infrastructure, for example, Snowflake, DeepSpeed, and Alibaba Cloud. Okay? And if you have any questions during my talk, feel free to interrupt. Feel free to raise your hand. Okay? So this seminar is for how long? It's 1 hour, 15 minutes?
45 minutes.
Oh, 45 minutes. So, okay. So probably I won't be able to complete all the stuff, but I will try. Okay? All right. So what's the problem that we're looking at? We all use Hugging Face, right? We use Hugging Face for uploading ML AI models, for downloading models, for model sharing. And Hugging Face is the world's largest and most popular model hub infrastructure. Okay. If you take a look at this result on the left-hand side, the X dimension shows the years moving from 2020 to the end of 2025. The Y dimension shows model count and also the aggregate model weight size in terabytes. So back in 2023, the aggregate model storage was only a fraction of petabyte, was approximately 0.28 petabytes. Then after 2 years, this number has increased significantly to a whopping 70 petabytes, okay? So this is an increase of more than 250 times. So we make an interesting observation. So Hugging Face model storage has been growing exponentially. So with such a growth rate, soon it will surpass this scale of one EB. So 1 EB is 1 exabyte, okay? By the end of 2027. So 1 EB is 1024 or 1000 petabytes or PB. 1 PB is 1024 TB. 1 TB is 1024 GB. So you can imagine the scale of Hugging Face. And this is ever increasing, okay? So to make things even worse, LLM training checkpoints are exploding as well. If you take a look at this result on the right-hand side, for the X dimension, it shows the model size in terms of the number of parameters. So we have these 3 different levels. We have 70B, we have 70 billion parameter scale. We have 405 billion scale. And the largest ever open weight model we have is 1 trillion, 1T, okay? So the Y dimension, it shows the size for both the model size and the checkpoint size in terms of terabytes. So if you look at the largest model with 1 trillion parameter scale, the model weight itself is only 2 TB. So how we calculate that is it has 1 trillion parameter, and assume each parameter is a BF16. BF16 has 2 bytes. 2 bytes times 1 trillion gives you 2 terabytes. But what is really surprising is the size of the checkpoint data, okay? So checkpoint data is 7.6 times larger compared to the model weight itself. The reason behind this is because it does not only include the model weight, but also include another significant module, which is called the optimizer state. So if you take Adam optimizer, which is the most popular optimizer that is used in all mainstream LM training. So it has 3 modules. The first one is called the master weights. The second, third are momentum and variance. So all these 3 modules, they use full precision, okay, which is FP32. FP32 has 4 bytes. So that gives you almost 8 times increase in size, okay? So this is not the end of the story. LM trainings are constantly generating tons of checkpoints data. So they need to frequently write checkpoints in order to provide fault tolerance. And checkpointing is one of the I guess, the dominating way of providing fault tolerance for LM training, in particular pre-training. And pre-training is super expensive. We all know about that. In order to train a large language model, it can easily cost like hundreds of millions of dollars, okay? And you really cannot afford losing any progress. And therefore, you have to use checkpoints, okay? So according to a study from Meta, for a massive scale GPU cluster, for example, 16,000 GPU cluster, it has an MTTF of approximately 186 minutes. Okay, so MTTF stands for mean time to failure. So what does that mean? That means that approximately every 180 minutes or so, there's going to be a failure, right? For example, a GPU failure or node failure, storage failure, power failure, or of any kind, okay? So if you don't want to lose, let's say 5% of your training work because it's super expensive, you need to checkpoint at least 20 times between failures within this duration of 186 minutes, okay? So that means the checkpoint interval is, if you do the math, 186 minutes divided by 20 gives you 9.3 minutes. You have to checkpoint every 10 minutes, every 9 minutes or so, okay? And that generates tons of data, massive amount of data, which is a whopping 2.4 petabytes. So these huge amount of data needs to be moved from GPU to somewhere to the global storage and needs to be stored somewhere at least for 1 day. Yes.
I believe AWS had something like snowmobiles or something. Does that help out in this situation where when the daily checkpoints explode or something?
so that Zoom people can do it.
Oh, yeah, sorry. So, that's for the Zoom people. Yeah, so does, in like, for example, AWS, don't you have to use like snowmobiles or snowballs in order to like, store all this, like, for example, the 2.4 petabytes in order to like, deal with like the explosion of like the checkpoints?
Yeah, so there are lots of different strategies in order to deal with this massive data explosion. But one way is this is the common practice. You delete data on a regular basis. For example, on the same day, all the checkpoints you saved within one single day, you save it only for one day, and then you reduce you start garbage collection on a regular like weekly basis and monthly basis. But still, you have to save tons of data because you want to do reproducibility, right? You want to debug the model, and you want to you just for the sake of records, you want to do different tests. So you got to save lots of checkpoints data, and checkpoint data is a bloating factor of this data amplification. Okay. Any other questions? Okay, so we got a very interesting and challenging research problem. Okay, so on the left-hand side, we have millions, if not more than tens of millions of users who are constantly uploading large language models to model hubs like Hugging Face. On the right-hand side, we have tech giants, model trainers, which are constantly and frequently store massive checkpoints across steps, across experiments, and across different versions, and so on and so forth. Okay, so at the end of the day, this massive amount of data needs to be saved somewhere, right? Effectively, we end up in a very interesting situation of what we call the AI model storage crisis, where the current storage demands are effectively unsustainable for massive AI models. So we are conducting research to address these research problems. So the rest of my talk is kind of organized as follows. Talk about a data analysis study first, and then I will present two major results if time permits. Okay. I will first present. The first result is ZipLLM, which is a model-aware storage reduction pipeline. And the second result is TensorDex, which is a tensor-centric lossless model compressor. Okay, so let's first take a look at the data analysis part. To better understand the real-world model storage. So let me try.
It's annoying.
Oops. No. I think it's above.
Oh.
So let me try this.
Yep.
Okay, there we go.
Thank you.
Okay, so we collected all the publicly available LLM repos from Hugging Face, and we conducted, to the best of our knowledge, a very first large-scale field study focusing on LLM storage characteristics. And we made two interesting observations. The first observation is fine-tuned LLMs, they are dominating. And the second observation is fine-tuned LLMs, they resemble their base models numerically, okay? So let's look at the first observation. So we all know about LLM fine-tuning, right? It's being very popular. If you want to customize LLMs, one way you can do is by using supervised fine-tuning, and the other way is reinforcement learning, okay? And fine-tuning has become a thing because of the rise of many open-weight LLMs that are released by major companies like OpenAI, Alibaba, and so on, okay? If you look at this result, it's another timeline chart. The X dimension shows the years ranging from 2019 all the way to 2025, and the Y dimension shows increasing trend. And we can observe that the fine-tuned LLM, so we have these two different groups of curves, right? One color-coded in orange, the other in blue. So these orange-colored curves represent the fine-tuned LLM increasing trend. And whereas the bottom one, the blue-colored curves, they represent the base models, okay? we observed that the fine-tuned LLMs, they are skyrocketing. They are outgrowing significantly faster compared to the base models. And base models are effectively just flattened, right? Even though it's still increasing, but it's overwhelmingly dominated by the fine-tuned models, okay? And the reason behind this is there are a very limited number of open weights and open source LLMs that exist, that are popular, which are used by the entire community for fine-tuning, for optimizations. And that leads to the first finding, that fine-tuned LLMs are dominating storage costs, and therefore, future system-level optimizations and data reduction optimizations should really be focused on here, okay? So for the next set of observations, we observed that fine-tuned LLMs, they basically resemble the base models. So here we conduct two set of experiments, which is shown on the left side of the slide. So for the top row, these three subfigures, so what we did was we took three fine-tuned models from a major LM family, which is Llama 3.1 8B. And then we performed this element-wise subtraction in order to calculate this element-wise delta. Okay, we do subtractions to subtract the weights from the fine-tuned model against the corresponding weight from the base model within the same LLM family. And these three charts, the X dimension shows the delta, the weight delta distribution, the range, and the Y dimension shows the distribution. So we can clearly see the distribution shape, right? It's very symmetrically structured. It's centered around zeros, which means that most of the deltas, they are zero or very close to zero. And the reason behind this is because the majority of the base model weights, they stay unchanged during the learning or the fine-tuning process, okay? So in contrast, we did another set of experiments, which is shown at the bottom. In this experiment, we took three fine-tuned LLMs from different families, from a neighboring family, from Mistral, okay? And we do the same subtraction against a base model from a different family, again, from the Llama 3.1 AB. This is a base model from a different family. And if you look at the distribution, the weight delta, delta W, it's from different LLM families are much wider, has significantly larger magnitude, beyond 5 in some point, right? This is significantly larger than the magnitude shown at the top slide, top figures, okay? And so we take the initiative and we draw this LLM family graph by using a new metric, a very simple metric of what we call bit distance. So by definition, bit distance means we just collect the average number of different bits between two different models, okay? So in some sense, it kind of resembles this classic metric of Hamming distance, okay? And we use it in a different context. Over here, we draw this LLM family graph by clustering different fine-tuned LLMs from different major LLM families. And we took these four major families. We have Queen 2.5, we have Mistral 7B, and we have Llama 3 and Llama 3.1, okay? And we can observe that within a single family, those fine-tuned variants, they have a very good clustering effect, right? Whereas cross families, we can see there's clear separation across different families. Okay? And for these two families, the Llama series, Llama 3 versus Llama 3.1, since these two, they come from the same, they're kind of relative, right? So they are close with each other. So we can see these two clusters, they are kind of mingled with each other, okay? And that leads to the second insight, the second finding. LLM variants within the same family, they are numerically similar, and therefore, they may benefit from a technique which is called delta compression, okay? And I'll be talking about how delta compression works in the next couple of slides. But are there any questions so far? All right, so motivated by insights, we built ZipLLM, which is a model-aware data storage reduction pipeline. But before delving into ZipLM technical part, so let me first talk about how Hugging Face existing data storage reduction pipeline works. Okay, so Hugging Face existing storage reduction, it has 3 different phases. So the first phase is what is called file dedupe. So how file deduplication works is it scans through the files across different repos and calculates the hashes, which is called fingerprints. And then it detects and removes the duplicate files with identical hashes, identical fingerprints. And that completes the file dedupe phase. And then it enters the second phase, which is called the chunk dedupe. So how chunk dedupe works is it uses a classic algorithm, which is called CDC. So CDC stands for content-defined chunking. How CDC works is it uses rolling hash to kind of determine the boundaries across different chunks. And then it splits the coarse-grained files into variable-sized chunks by content, okay? And then it detects and removes the duplicate chunks by comparing and scanning those fingerprints, okay? So this completes the second phase. And then it enters the last phase, which is file compression. So it just simply applies existing lossless general purpose compressors, for example, Z standard or ZSTD, or special purpose compressors like ZipNN, which is a model-aware neural network compressor for model storage. Okay. In contrast, ZipLM works in a completely different manner. So it synthesizes 3 completely different techniques. Okay, so the first phase, it tries to identify different LLM family information by identifying the LLM family lineage information, either from user-provided metadata, for example, model cars, or from self-defined metrics like bit distance. So once the family lineage information is identified, it enters the second phase, which is a deduplication phase. But in this case, we're not doing file dedupe, we're not doing CDC, chunk-based deduplication. So what we do is what we call tensor dedupe. So how tensor dedupe works is it naturally leverages this commonly used, extremely popular format, which is called safe tensors. And then it takes the index metadata out of safe tensors in order to identify the boundaries across different tensors, and then just directly apply dedupe on top of tensors. It brings 2 significant benefits, which addresses 2 severe problems suffered by existing CDC-based chunk-based dedupe. So the first benefit is it significantly reduces the metadata overhead because CDC works at extremely fine-grained chunks, ranging from a few kilobytes to tens of kilobytes. So for a massive scale model hub, if you have like billions of tensors with millions of large language models, you will have a metadata bloat problem, right? Then you need maybe tens of metadata server in order to host the entire index tree. And this is a big problem. So by using safe tensors format, by using tensor boundaries, you can reduce the metadata size by over 1,000 times. And the second benefit is tensor dedupe is inherently parallelizable. It can be parallelized in a very easy manner. It's kind of like tensor parallel scanning and tensor parallel I/O. And this also addresses a significant bottleneck for CDC because CDC is not parallelizable within a single file. Okay, therefore, tensor dedupe significantly increases the data ingestion throughput. The third phase is a delta compression phase, where we're using a new technique that we propose and design, which is called BitX. So I'll be quickly going through how BitX works in the next couple of slides. So how BitX works is it's super simple and yet very effective. So it takes 2 models. On the left-hand side, we have base models. And on the right-hand side, we have the fine-tuned LM variant, okay? And then it performs XOR operation, element-wise, bit-wise XOR operation to calculate the XOR. So XOR is inclusive OR. So how XOR works is the input data, if you have even number of ones or even number of zeros, the output of XOR is 0. Otherwise, if you have odd number of ones, the output is a 1, okay? So then you get the delta, which is a XOR result. And hopefully, this delta result is very sparse. By sparse, I mean it contains many zeros. The patterns of zeros is dominating, and that's how we call a sparse result, okay? And then it enters the second phase, the second step, where you just apply lossless compression. But before applying lossless compression, you need a small trick to kind of reorganize the bytes, okay? So take this BF16 data format as an example. So BF16, it has the most significant bit is a sign bit, followed by an 8 bits of exponent. And this exponent determines the magnitude of the value itself. And then followed by a 7-bit of mantissa. Mantissa determines the precision of this floating point. Okay? So by reorganizing the sign bit, by grouping sign bit with the mantissa, we effectively construct a byte, okay? And then we regroup by all the input data into a byte array. And then we apply a general purpose entropy encoder, for example, Z-standard, because Z-standard works at the byte level, okay? And that completes the BitX algorithm, okay? Yeah.
So there is a question from Jafar in Zoom. So AFAIK, so if you use a certain architecture without using its weights, Hugging Face still thinks it is a fine-tuned version of that model. So does this cause any problems?
Yes, I think this is a very good question. So this is actually a problem of ZipLM. So ZipLM relies on partially, even though partially, user provided metadata or Hugging Face provided metadata, okay? So if Hugging Face tells, hey, this LLM uploaded has a base model that points to, let's say, Queen 2.533B, so ZipLM would just do the delta compression against that particular base model. But this might not be the accurate lineage information, and that would lead to suboptimal compression ratio. And I'll be talking about this problem and how we address these problems in the third part of this talk. Okay, but this is a great observation. Any other questions? All right, so I'll quickly go through the evaluation. So to evaluate ZipLM, we downloaded, we randomly sampled like 3,000 Hugging Face LLM repos, which includes a bunch of major LLM families. And the 3,000 3,000 LLM repos is worth of around 43 terabytes in size, okay? And the result is showing this scatter plot. So the X dimension shows the data reduction rate, the higher the better. And the Y dimension shows the throughput, the compression throughput. Again, the higher the better. So as we can see, both BitX and ZipLM, they consistently outperform popular as well as the state-of-the-art data reduction method by a significant margin. Okay. So that leads us to the second major result. So I just talked about one problem suffered by ZipLM. And in fact, ZipLM has multiple inherent limitations. To address those limitations, we propose and build another system, which is called TensorDex, which is a tensor-centric lossless model compression method. Okay, so let me talk about several problems suffered by ZipLM. So the first problem, as I just mentioned, is about the metadata. So ZipLM assumes accurate model lineage information, okay? So it either takes metadata provided by the user, or it relies on a self-defined metric, for example, bit distance, which is not robust, okay? But reality is, real world LLM repos are very messy. It's either missing reliable metadata or it does not have accurate information at all. So to validate this hypothesis, we randomly sampled 500,000 LLM repos from Hugging Face. And out of these 500,000 samples, only 12.4% of them have usable metadata information. And even though within this small fraction of model repos that have usable metadata information, not all of them are accurate or consistent. So this is a problem, right? Because that might misguide ZipLM and lead to suboptimal data reduction result. So this is the first problem. And that also leads to the third finding, which is user-provided metadata is very unreliable or missing, which makes content-aware model-generated metadata a necessity. And this is what we do to address this problem. What's the second problem? The second problem of ZipLM is it assumes that all the fine-tuned LLM variants within a single model family, they get delta compressed against one and only one base model. So it basically assumes this single base delta compression kind of paradigm. So if you look at this example on the left-hand side of the slide, we have this base model, which is in the center. And then we have 4 other community-driven fine-tuned LLM variants, namely instruct, coder, instruct, and UI Gen, okay? If you just blindly delta compress all these 4 LLM variants against this base model, you end up having a very bad overall compression ratio, compressed size, which is around 71%, which means that at most you can reduce the size, aggregate size by 29%, okay? But the reality is, in real world situation, LLM lineage is rather complex. It's either chain or tree, it's hierarchical and multi-level. If you look at this example on the right side, so coder, this LLM variant is directly derived from base. But why you get this really bad compression ratio, this 79%, is because coder is rather special purpose, right? Because it used to generate code. And whereas the base model is general purpose, it generalizes, okay? So most of the parameters, when you do the fine tuning in order to train the coding LLM, most of the weights during the fine tuning process gets modified. So that is why you end up with this very bad compression ratio. But if you look at, if you look at this chain, so coder instruct, it gets directly derived from coder. So that is why if you delta compress coder instruct against coder, you end up having a compression ratio of approximately 50%. That means half of size can be compressed away, okay? So for UI Gen, you get even lower compressed size. The lower the better, okay? Which is a very impressive 34% of the compressed size, okay? So what does this result tell? It tells that real world model lineage information is very complicated. It's multi-level, it's chain-based, and it's hierarchical, and delta compression is highly sensitive to this model pairing. But without such an accurate lineage information, the XOR-based delta compression, it just fails to eliminate all this hidden, what I call the latent redundancy that exists across different models, okay?